Yes, so we are now within ergodic theory. So we started ergodic theory. The basic setup is more the measurable context. So we have a sigma algebra on a space X. We replaced the compactness that we had assumed in the topological dynamics discussion by assuming that the measure is a probability measure on our space. We have a measurable map from X to X. And we say that the measurable map is measure preserving, or that the measure is T invariant under the transformation. It's the same thing, coming from a different focus. If the preimage of the measure of a preimage is always the measure of the original set for any measurable set in our space. And one of the first results in that context is not hard at all, but it's surprisingly useful and surprisingly general, is Poincaré recurrence. It's called the recurrence theorem, so I should maybe say that, recurrence. We take our favorite probability space, our favorite measure preserving map on that space, and then we already have the conclusion that for any measurable subset, doesn't matter which measurable subset we take, almost every point within that subset will return to that set and will return to that set infinitely many times. And if you give me a counterexample, it's just a negligible point, right? Individual points are negligible, probably, depending on our measure, of course. If a point is not negligible, then it would have positive mass, right? And you can think about it, but whenever you have a point with positive mass, this needs to be a periodic point and it will return to the set because the point was in the set, right? Yeah, so usually we've been more interested in measures that don't have atoms, but it's not assumed anywhere as an assumption as of now. Yes, so I wanted to link it a bit more to topological dynamics and give you a corollary that, in a sense, strengthens the recurrence result we had in the topological dynamics discussion. So that's a corollary to the Poincaré recurrence. Let X be a compact metric space. B, the Borel sigma algebra. On X, mu, a probability measure. Defined on B. So it's a Borel probability measure. T, from X to X, measurable. Measure preserving. Then mu, almost every X in X is recurrent in the sense of topological dynamics. There exists nk going to infinity, a sequence of integers such that t to the nk applied to our starting point x converges back to the starting point. It's a bit different from what we had discussed in the recurrence theorem from section 1. it has, on one hand, weaker assumptions. We only assume that the map is measurable, but maybe also a bit stronger assumptions. We need an invariant measure already. So the question that this corollary sort of raises is, how do we get invariant measures? And we'll get to that. But right now, we just want to keep going, and assuming we have an invariant measure. We'll see some examples where this is easy to see that there are invariant measures around. And assuming that we have an invariant measure, the conclusion is sort of stronger than what we had in the first section. Because in the first section, we just said there exists a recurrent point. And we used Zorn's lemma to sort of find a minimal set, and then within the minimal set, every point was recurrent. Here we get a stronger statement. We get that for this measure, almost every point is recurrent. It's a much more concise, much better result somehow. Yeah, so I try to sell, maybe right now and also later on, the idea that ergodic theory in a sense is better than topological dynamics. It has stronger theorems, it has a better notion of irreducibility. Maybe you would say there is a notion of irreducibility also in topological dynamics. Like we said, the system is minimal if every orbit is dense. That's really sort of a smallest possible system, an irreducible kind of system. But what's missing is a theorem that says every system can be decomposed into irreducible ones. That's completely nonsense in the topological dynamics context. There is some theorem in ergodic theory that does that, and we'll see it a bit later, but I'm not sure whether we'll really prove it because it requires quite a bit of measure theory, quite a bit more than we are using today and in the coming weeks. Okay, so let's prove the corollary here. Let's stop the advertisement and just prove the corollary. As X is compact, X can be covered by finitely many. How many? I don't care, but it's just finitely many balls of radius 1 over n for every n in n. This way we get countably many balls. We apply the theorem to each one of the countably many balls. We apply the theorem to each of these countably many balls. And collect the null sets into one null set. Let X in X be not in this union. For this X that is not in the union of the null sets I constructed on the left here, I want to show that I can find this subsequence. By construction, X belongs to one of the balls of radius 1 over 1, and hence there exists n1 greater equal 1, so that t to the n1 x1 belongs to the same ball, and hence the distance of t to the n1 x to x is less than twice 1 over 1 times 1 over 1. Right, the diameter of the ball is at most twice the radius. And we do return to this ball, because if we don't return to this ball, the x would have been in the null sets that we collected on the left. And now we repeat the argument for the balls of radius 2 and find an n2 bigger than n1, because to the second ball we'll have also infinitely many returns, so we'll have a return that is later than the return n1. We repeat this for the balls of radius 1 over 2 and find n2 greater than n1 with distance t to the n2 x to x is less than twice 1 over 2, etc., etc., etc. We get what we want. Yeah, let's see some examples, some measures that are actually preserved by the dynamics, and we don't have to look very far. Example, a rotation by alpha on the torus is measure preserving. We take x and map it to x plus alpha. As always, our irrational rotation is measure preserving. If we use the Lebesgue measure, how do we want to write it? Maybe lambda on the torus. The torus is isomorphic, measurable. Measurably, it's the same thing as the 0-1 interval, half-open 0-1 interval. Yes?
How do you know up there that the ball of radius 1/2 is contained entirely in the ball of radius 1?
I don't know, I don't care. I just want to find, so the question was, why do I know that the second ball is contained in the first ball? I don't know that, but I don't care. All I care about is this inequality, which repeats again and again and again. Thank you. Right. This is not super surprising. Yeah, Lebesgue measure was always the measure that's sort of invariant under translation. That's its purpose in life somehow. Now it's on the torus instead of this whole real line, and whenever we move outside, we do a chopping and move it back in. Maybe there's a little bit of massaging to do if you want to prove it very formally, but it's not at all surprising. So let me just leave it at that. Are there others? Are there other invariant measures for this transformation? Yes, you have a...
I think if alpha is rational, we can
Yes.
take the point masses on the orbit.
Yes, and renormalize it to be a probability measure. Yes, very good. So the answer was very good. And for the record, if alpha is rational, then you have periodic points, and then on the periodic points you can find invariant measures again by renormalizing the counting measure. But if alpha is not rational, presumably this doesn't work, and presumably maybe there isn't any other. You could try to prove this. It's not impossible to do it now. It will be easier later. So I'll just make a comment. Alpha in Q. There are other measures exist. And alpha not in Q lambda is the only one. See you later. That has a name, and we'll talk about that phenomenon later. Let me do the other map on the torus that we like. TP from the torus to the torus takes x and multiplies it by p. P greater equal 1, an integer. Is measure preserving. For lambda, is it? So let's draw the graph. And, well, I draw it in a particular example. So maybe for p equals 3. So that would be the graph for T3. And you could argue, well, it doesn't look so measure preserving because it really stretches intervals, right? It is measure preserving. So why could it still be measure preserving even though it stretches intervals?
Integer, we repeat everything 3 times, and we actually only care about pre-images.
Pre-images, precisely. We need to look at pre-images, and pre-images shrink intervals, true, but it also creates 3 copies of the intervals, and that cancels. So if you take an interval here and take the pre-image, each one of these intervals is a third of the previous one, but together they have the same amount of Lebesgue measure than the original interval. So we need to keep using the correct definition, and in Lebesgue integration theory, always take pre-images, and that's why we stick to that. We always take pre-images. And it's good because it means that this is an example and not a non-example. So it is for measure preserving. Okay, maybe we need some checking. I'll write here a lemma, which shouldn't be terribly difficult to prove, but I'll write it down because it's helpful for these 2 examples. And we'll talk a bit about it, but we don't go now and start a measure theory course proving this. So let me just say the lemma and then indicate the main ideas for this lemma. If t from 0, 1, open or not open, it doesn't matter, to 0, 1 is measurable, and mu is a probability measure on the interval 0, 1, then it suffices to consider pre-images of intervals to verify whether t is measure preserving, mu is invariant. So just like in these 2 examples, we drew just an interval and said, it looks measure preserving now that we understand we have to use the definition correctly, but we still only looked at an interval and not just any measurable subset here and then the pre-image, which would maybe be possible, but would be a mess. And the lemma says we don't need to do the mess, we just need to look at intervals. It suffices. Yeah, it uses a bit of measure theory, and maybe not always the phrases are the same. So I'll give you the phrases that I'm used to, the way I'm used to measure theory being built up, but it might be that if you don't recall the names that I give you, that you might have to use some other names from your build-up, but never mind. Proof. Okay. Okay. We define C to be the set of all B in B, Borel sigma algebra of the interval, such that what we want is correct, right? Mu of T inverse of B is equal to mu of B. We assume C contains all intervals intervals, if you look at the, it's, if you have a disjoint union of elements in C, then the disjoint union will also be in C. Note, if Cn in C or Bn in B in C are disjoint, then the measure of the preimage of the disjoint union, preimage of a disjoint union is a disjoint union of preimages. Measures of disjoint unions are sums of measures. So this can go out and becomes a sum over all n of mu T inverse of Bn. But we said the Bn's are in this class of nice sets already. So here I can erase the T inverse and just say this is mu of Bn. And then I can again say the Bn's are all disjoint and convert the sum of the measures into the measure of the disjoint union. Which implies that the union over these things is again in C. So, and this even works for finite unions, but never mind. For countable unions, never mind that right now. So C contains not just intervals, it also contains finite unions of intervals. And if you take finite unions of intervals and look at this class of sets, that's an algebra. You can take unions, you can take intersections, you can take complements. So, yeah. Hence, C contains the algebra of finite unions of intervals. And here comes a nice fact. Moreover, or a nice definition, it's sort of often in measure theory, it's the definition that's the most important thing. And maybe here, think of it also this way. The definition that becomes useful is the definition of a monotone class. C is a monotone class. If I have a sequence of Bn's and the Bn's get bigger and bigger and the union of the Bn's is B and the Bn's are all in my class, then the limit is also in the class. And if the sequence is not increasing but decreasing, so here I have an increasing union of Bn's, here I have a decreasing sequence of sets and B is the intersection of them, then same conclusion, the limit is again in the class. And those are easy things because we are in a probability space and we have monotone convergence, and we have monotone convergence sort of in both directions because we're in a probability space. And then there's a theorem that says if you have an algebra and a monotone class containing an algebra, then this monotone class actually contains a sigma algebra generated by the algebra. So for me, it runs under the name of the monotone class theorem, but yeah, by the monotone class theorem, C contains the sigma algebra generated by the intervals. Which is the Borel sigma algebra of 0, 1. Done. Who has never heard of a monotone class? Okay. It's something that you can look up and learn. It's not terribly difficult. It's a way to build up towards Fubini's theorem. So in Fubini's theorem, you can use this because for rectangles, Fubini's theorem is trivial. And if you define the rectangles sort of in the measurable context, then the rectangles of finite unions of rectangles will form an algebra again. And then if you check that the sets for which Fubini holds is itself a monotone class, this can be very useful. So maybe you learned it under a different name or learned the various techniques towards Fubini theorems in a different manner. Then maybe those things could be used in the same way to prove the lemma here, but I'll leave it at that. Let me give you another example of a measure-preserving system. Sorry for recycling somehow. Here we had the rotation we had before, this guy we had before. Yeah, we can do higher dimensions and just say, let's take a toral automorphism, meaning an integer matrix, and maybe determinant plus minus 1. Or, never mind, it's just an example. I can do a concrete example. T from T2 to T2 defined by the matrix 0, 1, 1, 1. Is the map that takes a tuple of torus elements and sends it to x2, x1 plus x2, according to the 0, 1, 1, 1 matrix. Is measure preserving? With respect to lambda equals two-dimensional Lebesgue. On 0, 1 squared, which again, for the context of measure theory, I can identify with the two-dimensional torus. Right? This is a bijection, a natural bijection. But in the topological context, I wouldn't have written this down, or tried not to write this down. Maybe let's say it like this. I may have written it down and said it's not quite true. But now it's completely true that this is isomorphic because there's no topology anymore. That something converges here but doesn't converge here doesn't bother me because I'm just interested in the measurable structure. Okay. Yeah, why is it measure preserving? you could say it's just a substitution rule of Lebesgue integration in 2 dimensions. And it's even a much easier case because it's a linear substitution. And so you are interested in the Jacobian of the map. It's linear, so the Jacobian of this map is just the matrix itself and its determinant, or rather its absolute value of the determinant. And so it all boils down to the statement that the absolute value of the determinant is 1. Because the Jacobian equals absolute value determinant A is equal to 1, and T is a bijection. Right? I'm emphasizing that it's a bijection because I want to make the contrast to the TP map where we had the Jacobian equals P, but still it was measure preserving. But there was something different there, right? As we noted, it is P to 1, and Jacobian does something as well. And these two effects sort of cancel. Here, we have a bijection, and the Jacobian is 1. So it's a pretty straightforward case of the substitution rule. Again, maybe if you honestly want to write it down completely as a formal consequence of whatever kind of substitution rule you know for the Lebesgue measure in 2 dimensions, you may have to create some borders because, yeah, never mind. Yeah. That's okay. Okay. Yeah, of course we can also build other examples. Maybe I mentioned one. I could have this map, x1, x2 in the 2-dimensional torus, map to x1 plus alpha, not doing anything in the second coordinate. That's just the rotation, a fixed rotation on the horizontal coordinate independent of the y-coordinate. Or you could also do this. You could say x1, x2 in the 2 torus is mapped to x1 plus x2, x2. So again, the second coordinate will not change. And the first coordinate, I have a rotation, but what kind of rotation is determined by my second coordinate? So secretly, this x2 is like the alpha, but it's a different alpha for different x2s. And you could always ask, okay, is the Lebesgue measure preserved? Yes, it is. Yes, it is. And after you ask that, you can ask, are there other invariant measures that we can see? And in both examples, we'll see there are lots of them, right? You could just fix x2 and use a Lebesgue measure on the 1-dimensional circle in the x1 coordinate. Or if alpha is rational or if x2 is rational, you could have periodic points again. Same here, there are periodic points around, and with these periodic points you can create measures. But really there are many, many more invariant measures here. Yeah. But let's go back to the theory and start talking about the ergodic theorems, because it's called ergodic theory, so there should be some ergodic theorems. And yes, there are. But for this, let me define a notion that's kind of useful on occasions. It's called the Koopman operator. Let T from x to x be measure preserving. Then ut from L2 mu x to L2 mu x. Let's start to use a bit more measure theory. Defined by f is mapped to F composed with T is called the Koopman operator, called the Koopman operator. Another mathematician from last century, from the very early stages of ergodic theory, yeah, he started studying that, so in honor of they're named Koopman operators. And maybe we want to prove a few easy things about them, say a few easy things about this Koopman operator. It's an operator, so it suggests something. If you haven't had functional analysis yet, I tell you it suggests something. It suggests that it's a linear map. L2 is a nice space, it's a vector space, so hopefully this composition operator is a linear map. And that's, in some sense, quite amazing. No matter how crazy T is, it always gives you a linear map, because UT is a linear map. Yeah, T is just measurable, right? It's allowed to be very crazy. UT is a linear map. Of course, the vector space is rather large. L2 is usually very large. But still, yeah, it's not even a lemma. It's, yeah, observation claims. UT is linear, norm preserving, and inner product preserving. In L2. Yeah, linear does nothing to it. Let's do it. UT of alpha 1 F1 plus alpha 2 F2 is equal to, is the function x and x is mapped to alpha 1 F1 plus alpha 2 F2 at Tx, right? That's composing with T means. And at T, and the sum is defined, sum of functions is defined by spreading the sum around, right? So this is just alpha 1 F1 T of x plus alpha 2 F2 of T of x, which is just alpha 1 U T F1 plus alpha 2 U T F2 at x. So, as I said, it's not even a lemma. It's just checking definitions. So this function is equal to that function, which is what I claimed. Preserving the norms. It's not a lemma because we called it a lemma before, and it's a trivial consequence of a lemma before. So what's the norm of UTF? The 2 norm squared. By definition, that's F composed with T absolute value squared, d mu integrated over the whole space. But composing with T and then integrating with respect to an invariant measure, we had a lemma yesterday that says we don't need to compose with T, we can just integrate the original function squared. That's that. So it's preserving norms, it's linear. And it preserves inner products, same argument. Because if you take UTF1, UTF2, it's integral UTF1, which is F1 composed with T, UTF2, which is F2 composed with T, but conjugated d mu. And it's again, composition with T appears in the whole function. So I can simultaneously erase it everywhere, and I get the integral of f1, f2 conjugated, which is the inner product of f1 and f2. So how are these operators called, and why do I not call them like that? Preserving norm, preserving inner product, usually one calls that. Isometries is correct, but I wanted to search for a wrong word. Yes, usually one calls them unitary. Why do I not call it unitary? I should call it a isometry, that's okay. But I'm not allowed to call it a unitary. Yes?
Maybe it's not subjective.
Yes. Yes, thank you. That deserves one. Good. So if the T is invertible, if the T is an invertible measurable map, then there's also a UT inverse. And then it's rather trivial. I mean, UT is just composition with T. UT inverse is composition with T inverse. So if I compose these two things in one way or the other, I compose with TT inverse, which is called the identity, or T inverse T, which is called the identity. So if T inverse exists, then UT has an inverse and is a unitary operator. But in the example we had before about times P, that's not the case. There is no inverse map. And in this case, UT will only be an isometry, but will not be surjective. It will be an isometry from the Hilbert space into a subspace of the Hilbert space. Such things are easily exist, like in the TP map, it does precisely that. So let me comment that if T is invertible, so is UT, and in this case, UT is unitary. But yeah, maybe you said isometry, right? So that was a correct statement. I was just looking for a wrong statement. So yeah. Thank you. Let's take the break. Because the next thing is the theorem, and there's no point in starting writing this. Ready to state and prove our first ergodic theorem. That's the von Neumann mean ergodic theorem. Again, super general. Yeah, let X be mu, be a probability space, and T from X to X measure preserving. For any, or then for any F in L2, we define the ergodic averages of F, which is the average 1 over n, sum from k equal 0 to n minus 1 of F composed with t to the k. Yes. So that's called the ergodic average. And this converges, no questions asked. In L2, converges, and I can tell you what it converges to. Capital P, index T of F, in L2, meaning with respect to the 2 norm, where capital P index T is the orthogonal projection from L2 mu X onto the subspace I index t, which are all invariant functions. Of course, as n goes to infinity. Okay? And the proof is surprisingly easy. Again, 100 years ago, it was really easy to make an impact on that theory. And yeah, the proof is surprisingly easy. We just need a little bit of terminology, not even much technology from functional analysis. We just need a bit of terminology from functional analysis, which I think you all have seen before, right? I mean, in analysis 3, you're discussing anyway a little bit of Hilbert spaces now, and we are using Hilbert spaces now a bit. Yes. For F in this subspace, we have F composed with t to the k is equal to F, and hence n of F equals F, converging to F, which is also the orthogonal projection onto the subspace because my function is in the subspace. Et voila, right? So there we already have convergence. There's a second case that is about as steep as this one, meaning not very much. And then we'll build our whole theory onto these two subcases somehow. So we define B, another subspace, namely the subspace of functions of the form h composed with t minus h, where h is an L2. All differences, h composed with t minus h. This is sometimes called a co-boundary. We don't need that terminology, but it couldn't hold back. It has a name. Yeah. We take this thing and check whether for these functions it's also true. In this case, we take an of h composed with t minus h. That's the ergodic average. Sum from k equals 0 to n minus 1. H composed with t minus h. And then the whole thing composed with t to the k. But I can bring the t to the k inside because we said composing is linear. So I get here k plus 1, and here composed with t to the k. And then this is a telescoping series, which you have seen in analysis 1 already. And it simplifies to 1 over n, h composed with t to the n, minus h composed with nothing. And h is an L2, so it has a finite L2 norm. H composed with t to the n has the same L2 norm. So this has maybe twice the L2 norm of h, worst case scenario, and we divide this by n. So this converges to 0 in L2 as n goes to infinity. So for these two types of functions, for invariant functions and for these co-boundaries, it's a triviality. Maybe it's why is this the right limit? But that will follow immediately when I put down a claim that links this to the general case. Claim. We want to sort of use these two cases and get the general result. And the claim is that the orthogonal complement of B is this invariant subspace. B is a linear subspace, but it's not closed. Nobody said that. So if we know that and use Hilbert space technology, then we get that L2 is the direct sum of the space of invariant functions for which we know the theorem and the closure of B. Okay, so we'll use this and the two cases afterwards, after we prove the claim, to then prove the theorem from the claim. Okay. So there are two things to check, right? It's an equation, so we prove two inclusions. So we first show that if we have B, let B, H be in L2, and F maybe in IT, then I'm calculating the inner product of H composed with T minus H and my F. This is an element in B. This is an element in IT. So if my claim is true, this better be 0. And if I can show that this is 0, I've showed one inclusion, namely that one inclusion. So what do? I open, of course, the inner product. But leave a bit of space, because F is invariant, so I can put here composed with T, because I want to. And when I do that, I can use that my composing with T operator preserves inner products. So then this inner product is the same thing as this inner product. Right, so allowed. And this is equal to HF. So this whole thing is 0. Therefore, IT is contained in the orthogonal complement of B. If F is invariant, it's orthogonal to all of B. I now need to show the opposite. So I assume that I have something that's orthogonal to B. I need to show that it's invariant. So that's, yeah, 1/2, 1/2. And now we have 2/2. Suppose, yeah, let's call it again F. F is in the orthogonal complement of B. And H is in L2. Then I know that my H composed with T minus H inner product with F is equal to 0, right? That's what I know. I can rewrite this in the form that UTH inner product with F is equal to inner product of H with F. Now I take the adjoint of this operator. UT, we said, is a nice operator, so I can take its adjoint. You have seen that? Who has not seen that? Okay. So you have seen it in linear algebra. In linear algebra, you discussed matrices in the context of inner products. Linear algebra 2, probably, maybe. And there was an adjoint operator, which is just transpose conjugated for the matrices. In the Hilbert space, it works similarly that for any bounded operator, any operator that like is an isometry maybe, or has bounded norm, one can find another operator that is sort of written over here and has the same inner product. So this is by definition the same, by definition of the adjoint operator, the same thing as ut star H inner product ut star applied to F. Let's make the compromise that I now keep going. And if someone wants to find out a bit more, we can talk about it after the lesson is over. So this was my assumption. F is in the foreground complement of B. This I can rewrite like this using my operator, my Koopman operator ut. And the Koopman operator is a nice operator. It has an adjoint operator, which I can write on the other side of the inner product, and it would still be okay. And that's now true for all H in L2 mu x, which is weird because that's only possible if this function is equal to that function. For all H in L2 mu x. Which implies ut star of F equals F. Let me open a parenthesis, which is easier to understand, but it's not the general case. If T is invertible, I can tell you what ut star is. It's the Koopman operator for T inverse. And then we get the conclusion that we want. But I shouldn't assume that because I didn't have this as an assumption. I didn't have an assumption that says T is invertible. But let me open this parenthesis just so that we have a case that is completely understood, even if you don't know what the adjoint is yet. If T inverse is a measurable map, then ut inverse exists, and ut star is actually ut inverse. Let me verify that this is the case. So I had H composed with T, F nothing, right? And I wanted to rewrite this in some sense. But of course I can write composed with T inverse, composed with T, because that's just composing with the identity. And now I have composed with T twice in the inner product. And we said composing with T preserves the inner product, so I can rewrite this as HF composed with T inverse, which is now saying that UT H F is equal to H UT inverse F. So the UT star, the mystery operator from above, is just the unitary operator composing with T inverse. In this case, UT, this formula here that I got is UT inverse F equals F, means F composed with T inverse is F, and equivalently F equals F composed with T, which is what I wanted to show, because I want to show that the F that is in B orthogonal is actually in IT, second inclusion in my claim. Right, so I wanted to do this parenthesis anyway, so if you haven't seen the adjoint yet, then this extra assumption makes it clear what's happening. But I'll continue now the proof without this extra assumption and want to get to the same conclusion using this formula. In general, we obtain now, I want to know the distance between F and UTF. And I'm in the Hilbert space, so I look at the norm squared. I write down the definition, F minus UTF, inner product with F minus UTF. Open the inner products, I get 4 expressions. F with F, plus UTF with UTF, minus F with UTF, and minus UTF with F. Those are the 4 expressions I get when I open up everything. This here is the norm of F squared. This here is the norm of F squared because UT is preserving the norm. So I get twice the norm of F squared minus, and here do what the adjoint is for. The adjoint is for taking the operator and moving it over to the other side. So I get minus UT star F, F minus F UT star F. But wait a moment, I already said before that UT star F is F. So this here is just the norm of F. And this here is just the norm of F. So this whole thing is 0. Which means that this funky statement implies the statement that I want, namely that F is equal to UTF. Hence, F composed with T is equal to F, and F is in the space of invariant functions. This proves the claim. You're allowed to ask questions. Right, so the functions in B are precisely of that form. If I take a function in B and an invariant function, I can open up the parentheses, put here because of the invariance the composed with T, and get that the inner product is equal to 0. So that shows that invariant functions are orthogonal to functions in B, so that's 1/2 of this inclusion. And it was this inclusion, invariant functions are orthogonal. Now I take, in the second half, I take a function from the orthogonal complement and want to show that it's invariant. So I take a function. When I say function, it's kind of cheating, right? It's always an equivalence class of functions. I take here an equivalence class of functions from the orthogonal complement and an H in L2 that defines an element in B. And by assumption, I know that the inner product of this H composed with T minus H with F must be 0 because my F is in B orthogonal. I rewrite this in general using the adjoint operator, H inner product with UT star F is equal to H inner product with F. And whenever I have such an equality for every H in the Hilbert space, then the two things here need to be the same. Formally, you can see this by moving the inner product again to the other side, writing it as one inner product, and then you get a vector that's orthogonal to everything. But orthogonal to everything is also orthogonal to itself. And if you're orthogonal to yourself, then you must be the 0 vector. So then this vector needs to be that vector. So that's what I said here. And up there, there's a small calculation which then tells you that if ut star f is equal to f, then actually utf is also equal to f. And this gives us the second inequality, and hence we know the claim. The second inclusion, and hence we know the claim. So I'm erasing the proof of the claim, and we keep going towards the theorem. Okay, let f be in L2 mu x arbitrary, and using star, we can find f star, which is the orthogonal projection onto this subspace of invariant functions of f, and some, let's call it g, in b bar, so that my f is equal to f star plus g. Let epsilon be greater than 0, because we want to show a convergence. Then there exists some h in L2, so that g minus h composed with t minus h is less than epsilon. Because that's an element in B, and my element G is in B bar, so it's in the closure of B, so I must be able to approximate this other element G by an element from my subspace B. And I've chosen approximation epsilon. Why not? And now I just brute force, I'm interested in the average of F, and I want to compare it to F star, and use what I got together with good properties of the averaging. So it's an average ring operator somehow, and we'll use that it makes norms smaller, not bigger, because it's an averaging. We'll see it. We now have, I'm interested in the ergodic average an of f minus f star, which is the orthogonal projection of my f, which is an of f plus f star plus g, right? Because my f is f star plus g minus f star. And that's always 2 norm. But the averaging is obtained using the composition operator, and the composition operator was linear, so the averaging operator is linear. So I can average the one function, and I average the other function and separate the 2 expressions. So I get an of f star minus f star plus an of g, 2 norm. But f star is invariant, right? So when I compose it with my transformation, nothing happens. When I average, nothing happens. So this is 0 here. So all I'm doing is I'm looking at the averaging of the function in the orthogonal complement of the function in G bar, in B bar. Okay? But I now add and subtract my function H composed with T minus H. So plus AN H composed with T minus H minus AN. Well, maybe I do first the minus and then the plus, it doesn't matter. So this H composed with T minus H is kind of one function that I want to use. So again, it's a linear operator. I rewrite it one more time, and then I go back to the definition. So I write it as AN of G minus H composed with T minus H plus, and maybe use the triangle inequality less or equal, AN of H composed with T minus H. This here, we already established converges to 0. We know that. That was the telescoping case. So we can make this less than epsilon if we want. For large enough n, this will be less than epsilon. So let me, I'm almost done, but I need a bit more space. That's equal plus epsilon from this for large enough n. And this I'll open up, and I guess you again use the triangle inequality because it's an average 1 over n sum k equal 0 to n minus 1 of G minus H composed with T minus H composed with T to the K and the 2 norm of that. Right, because the average contains precisely these expressions without the norm. And I just use properties of the norm to rewrite the norm of the average as the upper bound average of the norms. But composing with T to the K doesn't change the norm. Don't need to write that. And this is less than epsilon because that was my choice of my H. That was my approximation. So I'm averaging epsilon, something that's less than epsilon, so I get something less than epsilon. So this is less than 2 epsilon for large enough n, which is what I wanted to show because it's really telling me that the ergodic averages converge to the function f star, which is the orthogonal projection of f onto the space of invariant functions. Okay. It's kind of very geometric, but geometric in the sense of Hilbert space technology, right? We just needed to decompose our Hilbert space in the right way, and we got to where we want. It's so this next theorem is again an ergodic theorem. We don't get to it today. It's called the Birkhoff pointwise ergodic theorem. Because our current theorem has an issue. It's convergence in L2, right? What does convergence in L2 mean? It means what we showed, that the L2 norm converges to 0. It does have pointwise consequences. Every time you have a convergence in L2, there exists a subsequence of times so that for that subsequence you have pointwise convergence almost everywhere. That's a general fact that always exists, but it's kind of not so nice that you look at the ergodic averages and we might have to take subsequences of the times to obtain an almost everywhere convergence of the ergodic averages to a function. That doesn't sound so nice. And if you now take a different function, there might be a different subsequence. It's not so great. So what you rather would like to say is, given a function, we can look at the ergodic averages, and the ergodic averages converge almost everywhere to a limit function, which is nice. That's the much better statement, and that's the pointwise or individual ergodic theorem, and that's the theorem of Birkhoff, also from around that time. And there's actually a controversy somehow. It's not a nice story. Not nice for Birkhoff, because he was a bastard. He was, sorry, excuse my language. He was older than von Neumann. I mean, in hindsight, von Neumann didn't have a problem, right? His career was fine. But he was younger at that point, younger than the two, and Birkhoff was an editor of a journal. And von Neumann had found his theorem, wrote it up, and submitted it to the journal. And then Birkhoff was sort of not holding this paper back until he was finished with his theorem and could send off his theorem as publishing first or something. Not so nice. It's not politically correct. It's a nicer theorem, but there's also a claim that somehow the pointwise statement is much less stable. The proof is a bit harder, and it's so for physical intuition, physical context, somehow the claim is that the von Neumann theorem is anyway the more relevant one. It's more stable in many aspects than the pointwise result. Anyway, both theorems are cool theorems, and the pointwise statement is stronger in many ways anyway, so he could have just had the other thing published first, and would have not been an issue for Birkhoff. Never mind. Yeah, we need a bit of preparation, because the Birkhoff theorem in its full glory is a theorem for L1 functions. L1 functions are a bigger space because we're in a probability space. Every L2 function is an L1 function in a probability space. You just need to think about it, then you will know where it's true, but it is true. So if we have a theorem for L2 with two convergence in L2, it doesn't necessarily tell us something about L1 functions, except that it does tell us something. We will use it to prove the L1 convergence. Yeah, but never mind that. But what is the replacement of the orthogonal projection? That's what I want to get at. That's a preparation that we should talk about before we do the pointwise ergodic theorem, because if we can't give the limit a name, then what is the theorem about? It's much better if we first talk about the terminology, then we have a name for it, and then we can keep going. So it's kind of a lemma plus definition that we need to do before, and I'll state it, and then we discuss it, whether you've seen it. Let X be mu, be a probability space, and let A in B be a sub-sigma algebra, a sigma algebra in, yeah, sub-sigma algebra. Yeah, maybe I was missing a little tiny point in the discussion up there. An exercise is to check that IT is a closed subspace. It was kind of implicit. I did the bar on the B, because B is not a closed subspace, but I didn't do the bar on the IT. So you should check. I'm not going back to its exercise. Check that IT is closed. It's not hard. You can use the operator UT, and it shouldn't be hard. Never mind. let's go back to the L1 story here. So we have a sub-sigma algebra. Then there is an operator for L1 functions that behaves like the orthogonal projection. So that's not how I write it down, but I'll write it down. Then there exists an operator. So it's linear and has some norm properties. Exists an operator which I call E, parentheses, placeholder, vertical line, given, which I read as given A. So this is conditional expectation of a function given A. That's how I read this, which is an operator from L1 mu xb to L1 mu xa. Which takes a function and sends it to its conditional expectation given A, which is a function again on X. And you should think of it as a little bit like a projection onto the subspace of A measurable functions. And this operator has some properties, some of them nice and some of them characterizing, so even nicer. So it's linear. E something A is linear. It may not preserve norms, but it doesn't increase norms. So E FA, the one norm of it is less or equal than the one norm of the original function for F in L1. So that's also called the operator norm of the conditional expectation operator is 1. It's equal to 1 because for a constant nothing will happen. Constant is mapped to itself, which will be clear once I wrote down the characterizing property. It's clear here, but I write it down because it's really important. The image function is A measurable because it's an element from here. It's A measurable. If F is positive, then the conditional expectation is positive. If G is an L infinity A measurable function, and F is an L1 function with respect to B, then the conditional expectation satisfies some kind of linearity for the A measurable function. I can take this G and put it outside the expectation. And now the characterizing property. For F in L1 xb mu and A in A, we have, when I integrate the conditional expectation over this A measurable set, I get nothing new. I get the old integral. The last thing you could maybe think of is a bit like the orthogonal projection statement, right? Because integrating over A is like integrating against a characteristic function. And you have before projection and after projection, you have the same inner product. So this you should think of as an L1 version of orthogonal projection. And yeah, the whole of conditional expectation is an L1 version of a projection. Yeah, I said it, maybe I write it down. Conditional expectation given A. Yeah, I'm not finishing today with this. Who has seen something like that? Okay, so some of you have seen it, yeah. So martingale theorems, someone has seen, yeah. So this is sort of the starting point, and then one can produce more and more theorems out of it. And there are two martingale theorems, increasing and decreasing martingale theorems, that take this as an input. And one of them, I forget, no, I don't forget. The decreasing martingale theorem is by itself like an ergodic theorem. There are cases where the decreasing martingale theorem is an ergodic theorem. So it's not unrelated, and sometimes these martingale theorems are also useful. We might need them. If we need them, we will discuss them. But yeah, now we are interested in that thing. There's more than one way to get this operator, or to get this conditional expectation of a function. Maybe before I say that, this formula characterizes the A measurable function on the left. That's sort of an easy thing for measure theory, that if you have two functions that are, say, positive, and the integral over all subsets of the one function and the other function are always the same, then the two functions are almost surely the same. Assuming the sets that you integrate over are measurable with respect to the same sigma algebra as the functions that you're using. So if you have two versions of the conditional expectations, this formula tells you that the two versions are actually the same function almost everywhere, if both of them are A measurable. But you can't apply it sort of with this function on the left and that function on the right, because F is B measurable, not A measurable. So this uniqueness statement, easy uniqueness statement for measure theory, doesn't apply here, because you're having A and B around. And that's precisely what this operator does. It sort of makes the B measurable thing. It does some kind of averaging in the space to make the B measurable thing a bit more constant in certain directions of the space, to make it A measurable. And then it's uniquely determined by this formula. And I can draw you sort of cases where it's very clear what the conditional expectation is doing. But in some sense, the purpose of the lemma and the definition is precisely its abstractness. That we can have this conditional expectation operator even if we have very little idea what the A is. It always exists. That's the beauty of it. So for instance, if we don't really know what the invariant sets of invariant sets is, the sigma algebra of invariant sets is, if you don't have any clue on that, it still gives you an operator. Yeah. So the case where it's easy to figure out what the conditional expectation is doing is if you take, say, the Borel sigma algebra cross the trivial sigma algebra in a product situation. And you take a product measure, then the conditional expectation is doing something, and what it's doing has something to do with Fubini, no surprise. But if your measure is not a product measure, then it still exists, but it may not have anything to do with Fubini anymore. Good. Thank you.